Obviously, by definition, f plus g of 2 will be f of 2 plus g of 2. And you're right, f of 2 is 7, right? And g of 2 is -1. So this is 6. Right?
Yes.
Good. Now, what about g comp f? Again, I have to write g of f of 2. F is the inner. F has to be evaluated first. And I have that f of 2 is, so then I'm really asked to find g of 7 and nothing else. How much is g of 7? That's it. Perfect. Uh, 12.2, inverse. Is this clear? You want another example, Heather?
No, that's okay.
Inverse functions. Okay. Let's suppose I'm looking at the map and to find out how to get from here to New York. That's one function for me. One task, one function. I have an input, I have an output. I want to get from here to New York. But I also want to come back. That would be my inverse function. I want to retrace my steps and come back. That's pretty much the concept of the inverse function. Meaning, if I apply to x equals 2 a function f and I get y equals 3, I want to be able to apply to y equals 3, which now will become x equals 3, to this function that is denoted like this. It's not 1 over f. It's the name of this function is f inverse. The inverse function of f. Because we just discussed today an example in which we had a to -1. And we know that a to -1 is 1 over a. But this is not the case. This is just a name of the inverse function. So if the function is applied to 2 and returns 3, when I apply the inverse procedure or inverse function to 3, what should I get back? If this is indeed the inverse function of that. Exactly. So if the function has the ordered pair 2, 3, what will be exactly the ordered pair for the inverse function? 3, 2. So now we understand that the domain of the inverse function, the domain and range of the inverse function are reversed domain and range of the function. Let's go back to functions for a moment, because not all functions have inverses that are functions. So when we discussed functions, I presented different examples. Okay, let's identify some of these functions. We don't know all of them. This one we don't know. We have never studied it. But we studied this, we studied this, we studied this, and we studied that. What is this one? Very good. This one we don't know. It's for later. I know this one. Very good. I know this one. Very good. And I do know this one. Very good. Excellent. Well done. Okay. Now, are all these functions? Yes. By the vertical line test, they are all functions. Now, the question is, if a function is not what we call one-to-one. We had, I'll come back to the graphs in a second. We had three situations. We had this situation, which is a function. We had this situation, which is also a function. And we had this, which is not a function. This one is so-called one-to-one. Why? Because when I go back, if I want to go back, that's the idea. This is the domain and this will be the range. I can. It's still a function. This one, it's not one-to-one. Because if I try to go back, it will be like this one, which is not a function. So this one is one-to-one, meaning not just to one x, one y, but also to each y, only one x. Only one-to-one functions have inverse functions. This is not one-to-one. It will have an inverse, but it will be a relation, not a function. So one-to-one, not one-to-one. And then I would like to write this, and I'm coming back to the graphs. Note, only one-to-one functions have inverse functions. Everything has an inverse, but it's not going to be a function if the initial function is not one-to-one. So coming back to our graphs, I know this is a function, but now I'm testing whether it's one-to-one. For this y value, let's say 5, how many x values do I read? 2. So for this y value, I read 2 x values. Is it one-to-one? No. Not one-to-one. What about this one? For this y value, I read this, I read this, I read this. Is this one-to-one? No. What about this? Yes. What about this? So this was not going to have a function. That's the inverse. What about this? So when I check whether a function is one-to-one, I'm looking at the graph and say by the horizontal line test, it is or it is not. There are other ways if I'm given the algebraic expression. If I'm given, for example, let's say f of x equals 3x minus 1, I'll say linear. Always one-to-one. If I'm given f of x equals the square root of x minus 1, I'll say square root. Always one-to-one. But if I have f of x equals x squared plus 2, I'll say not one-to-one, because I have the picture in my head. If I'm told f of x equals the absolute value of x minus 3 plus 10, I'll say not one-to-one, because it's a v function. So I have ways, and in other situations, there is a procedure, but it's not in your section, in the section here. So I would like to look at how to determine the one-to-one. So I know that, how to determine the inverse, sorry. So I know that this function is one-to-one. It has f inverse. Find f inverse for f of x equals 3x minus 1. The procedure has 4 steps. Like completing the square has 4 steps. The middle coefficient divided by 2 square and then add to both sides. Same thing, not similar, but 4 steps. Step number 1, replace f of x by y. Can I do that? Yes, f of x is the same with y always. So in this equation, I will write y equals 3x minus 1. Second step. And you will tell me whether this is allowed. Interchange x and y. In other words, I see y, I put x. I see x, I put y. And before you answer, allow me to go back to that little chart. This y becomes x for this function. So that's why I changed the notation from y to x, because eventually I want to determine this that will become y. So that's the reason why I'm allowed to interchange the two. In step 3, I solve for y, because this y will become f inverse. This is a linear equation. How do I solve for y? I add, and very good. So y equals x plus 1 divided by 3. And the procedure is done. In step 4, I have to replace y by what? By what I'm looking for. F inverse of x equals x plus 1 divided by 3. It's a 4-step procedure for finding f inverse. Let's find f inverse for f of x equals the square root of x minus 1. Same 4 steps. So in step 1, I have y equals the square root of x minus 1. In step 2, I have x equals the square root of y minus 1. It's a radical equation. I know how to clear the radical by squaring both sides. So then I have x squared equals y minus 1. Therefore, y equals x squared plus 1. And this is my f inverse. However, there is a situation here that I have to explain. What is the domain of this function? Remember, I have to write that x minus 1 must be or equal to 0. So then x greater or equal to 1. So this is 1 to infinity. Now we know the picture. So this is the square root of x. But since it's shifted to your right once, it starts at 1. From 1 to infinity. Correct?
Yes.
Perfect. What is its range?
0.
Very good. Perfect. What will be the domain of this function? It must be the range of the original one. Mandatory. Right? So remember this. If this is 1 to infinity and this is 0 to infinity, what is the domain of f inverse? That's all I have. And what will be the range of f inverse?
1 to infinity.
So I have to be careful because remember x squared plus 1 is this up 1. But this is not 1 to 1.
Yeah, no, it's not.
Right?
Right.
So that's why the domain must be only 0 to infinity and the range is 1 to infinity. So how will this look like?
Interesting.
Is that clear?
Yes.
Because I cannot accept everything. If I accept everything, its inverse will not be this.
Right.
So they are tricky. They are tricky.
Yeah.
Very good. Here's the question now. I have determined, let's say the first function was f of x was 3x minus 1. And its inverse, you determined it with me, x plus 1 over 3. Now I'm asking you, just to have an idea, just a gut feeling, what will happen when we do or perform the function composition that we just talked about, in any direction you want? Let me give an example before you answer. Do we agree that multiplication by 2 and division by 2 must be inverse operations? Or even, let's say, even a simpler situation. I give you $10. So this is f plus 10, x plus 10, right? You have whatever, and I'm giving you 10. But then I'm taking it back. Are these two operations inverses of each other?
Yes.
Giving you 10 and taking it back from you?
Yes.
What happened to your x?
It stayed the same.
So what happens when I apply the function composition in any order? I apply f, and then I apply f inverse. Or I apply f inverse, and then I apply f. They must cancel their effect on one another. Giving you 10 and taking it back from you didn't give you anything. No change.
Right.
So the function composition in any direction, if these two are inverses of each other, what should
It's
be?
equal to X.
That's it. So this is the property of inverse functions. This will not happen if these two are not inverses of each other. Let's test. Let's test our f inverse to make sure that this is the correct inverse. Or we can work on a different problem. I can choose a different problem. Like, for example, we are given two functions. We are asked, are they inverses of each other? On page 728. I'm changing the requirement a little bit. I just want to show we are given f of x, which is 3x minus 10, and we are given g of x, which is x plus 10 divided by 3. The question is, are they inverses of each other? And then if they are, I would like to graph them on the same coordinate system. Are they inverses of each other? I have no idea. But I know that I have to calculate f comma g of x. I have to calculate g comma f of x. And if both turn out to be exactly
Perpendicular.
x,
X.
then they must be inverses of each other.
Right.
Otherwise, it will not happen.
Right.
If they are not inverses of each other, I will never get plain x. I will get x squared, I will get x plus 5 over 2, I will get x cubed, but not plain x. Exactly. So f comma g equals f of g of x, which is,
X plus 10 over 3.
with, yes, f of x plus 10 over 3, but now f is f of 3 times whatever minus 10. The whatever is x plus 10 over 3. I simplify 3 and 3 because there is a 3 times whatever, and this is my whatever now. 3 times whatever minus 10. 3 and 3 go away. I have x plus 10 minus 10, so the answer is
X.
x. If this direction is x, the other one must be x. Do we have to show the other one? Yes. If this direction is 5x, I don't have to show the other one. I don't care what I get for the other one. They are not inverses of each other. But once I got that f comma g is x, I still have to show the other one, although I know it's going to be x. So the other one is g of f of x, which is g of 3x minus 10. And I look at g. G says whatever, which is 3x minus 10 plus 10 divided by 3. I simplify the 10s. Then I have 3x over 3. I simplify the 3 because they are factors. And the answer, as expected, is x. So what do I conclude about f and g?
That they are
Inverses of each other. So if you want now, you can say, I know this is f inverse. It cannot be anything else. So f and g are inverses of each other. Otherwise, the x will not happen. Okay, now I would like to graph them because there is one more conclusion here before we continue. I'd like to graph these two on the same coordinate system to see the relationship between the two graphs. I want to draw a conclusion. So I'm going to graph this first. It's a linear function. This is y equals 3x minus 10. When x is 0, y is negative 10. And that's, I don't like it. It's too squeezed in there. So I'm going to go to the next page. Sorry about that. X equals 0, y equals negative 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And when y is 0, I get 10 over 3. Tough. But it's a little bit more than 9. It's a little bit more than 3. 9 divided by 3, right? So 1, 2, 3, right here, let's say. I draw the line. So this is f of x, which is 3x minus 10. Without doing anything, I would like you to give me two ordered pairs that I will use to graph the inverse. And no calculation is required. If the function has the ordered pairs 0, comma, negative 10, and 10/3, comma, 0, the inverse function must have so this one was, let's write it because it's difficult, 10/3, comma, 0, and this is 0, comma, negative 10.
negative 10 and 0.
Exactly. Of course. I don't need to calculate anything because I know there are inverses of each other. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that would be negative 10, 0. And the other ordered pair will be 0, comma, 10/3. Now what I want you to notice, so this is f inverse x plus 10 divided by 3. What I want you to notice is this. See that this is a reflection, right?
Right.
This and this are reflected with respect to this line. This and this are reflected with respect to this line. If I fold it, this should overlap with this, and this should overlap with this. What line is this? They are symmetric, you're right, with respect to this line. Notice that this has to be at the same point, because here x and y are the same. So then we'll write a note. What line is this? The simplest possible linear equation. Exactly. So this is our note. Note. The graphs of f of x and f inverse of x are always symmetric with respect to the graphs of f of x and f inverse are always symmetric with respect to the line
Or y equals x.
always. Always. Any questions? So far we did a lot. We learned how to find the inverse function. We know how to graph the inverse function. We know that if the function f is defined on set A, taking values in B, then the inverse function is defined on B, taking values back to A. We know that their graphs are symmetric with respect to the line y equals x. Any two inverse functions will, if you graph them on the same coordinate system, they will always be symmetric with respect to y equals x. Okay. Now, the last three sections deal with those three functions. So what we covered so far, so we know, oh, I'm going backwards, of course. How long ago was this? Okay. So this was the algebra of functions, function composition in inverse functions. So now we are going to learn about the last two functions in this course. We look at the exponential. And that is section 12.3. Exponential function. First question I have is, going back to these graphs. A few minutes ago we listed a bunch of graphs. Okay. Why is this called linear? Because it's a line. Why is this called absolute value? Because. Why is this called a square root? Because it has a square root. So my question here is, why do you think this function is called the exponential function?
Because it has exponent.
Right. And the exponent is the variable. Very good. So a function that has a constant as the base and the exponent as the variable is called exponential. Because the variable is the exponent. Okay. Now, A, which is the base, cannot be 0, cannot be 1, and it cannot be negative. And you can say, okay, wait a minute, what can it be? So it can be two things only. A can be a tiny number between 0 and 1, not 0 or 1. Or A can be a number greater than 1, not 1. And the obvious question is this. Why? Why the base cannot be 0? I can raise 0 to the 5th power and I get 0. Why the base cannot be 1? I can raise 1 to 10 and I get 1. Why the base cannot be -3? I raise -3 to the 2nd power and I get 9. All these numbers exist. So why does A cannot be 0, 1, or negative? Simply because its inverse function will not exist. Not because I cannot raise these numbers to powers. So the reason is, if we allow 0, 1, or negative, then the inverse function of a to the x will not exist. And this we will see it's a one-to-one. We will graph it, and it is a one-to-one function. Should have an inverse. Very nice and good function. Positive function in the sense that it's defined everywhere. It's not like the square root. It's not like the rational. It's a nice function. It's defined everywhere. Okay, so we have a shape with a base between 0 and 1, like 1/2, 1/3, 1/5. And we have another shape when the base is greater than 1. So this function will look differently based on its base. This will have one form, this will have another. So let's start with this. I know I'll finish with one of these two, and we'll continue on Thursday. So let's say f of x equals 2 to the x. Let's just graph this one and we'll stop. So let's look at the chart. Create a chart of ordered pairs. The domain is all in numbers. This is a nice function. Domain of f is -infinity to infinity. Anything goes. I can raise 2 to a positive number, I can raise 2 to 0, and I can raise 2 to a negative number. We had that example with 2 to a -1. So I'm going to just pick some numbers like -2, -1, 0, 1, and 2. So let's plug in 0. How much is 2 raised to 0? Careful. So 2 raised to 0 is 1. Let's prove that. How much is 2 to the 4th over 2 to the 4th? Don't calculate anything. It's 1, right? But it's the same when I copy the base and subtract the exponents. So that's why these two are the same. I know that 2 to the 4th over 2 to the 4th must be 1. But if I use exponential rules, I copy the base and subtract the exponents, and these have to be the same. So this is 1. Now 2 raised to 1. 2 raised to 2. Very good. The other way, 2 raised to -1. 2 raised to -2. Perfect. Now let's identify the endpoints. 1, 2, 4, 8, 16, 32, 64, 128, 10,000, 5 billion. Where am I going? Excellent. Now I'm going the other way. 1 divided by 2. Like I have $1 and I give you 50 cents and 50 cents. Then 1 divided by 4, you're getting 25, right? Divided by 8, you're getting even less. Divided by 16, even less. By 32, even less. By 64, by 128, even less and less. Exactly. Excellent. That's all I needed. So let's graph. From left to right, the first ordered pair is right. Difficult to plot, but we'll figure it out. Something like this. Next ordered pair, -1, 1/2. Somewhere in the middle here. Next one is comma 1. And then 1, comma 2. And then 2, comma 4. This has the fastest growth possible. And this is the function 2 to the x. So some students ask me in the middle of the semester, hey professor, can I still get an A in the class? And my answer is yes, as long as your grade from now on follows an exponential function with a base greater than 1, then you will. And some of them say, huh? I said, look it up. Is this function 1 to 1?
Yeah.
Then it has an inverse function. I don't even know what the inverse function is all about, but I can graph it. Can you please give me a couple of points that will help me graph the inverse function of 2 to the x?
1 and 0.
You will say 1 and 0 because you are reflecting this over y equals x. Excellent.
2 and 1.
2 and 1. So 2 and 1. Excellent.
4 and 2.
4 and 2. Excellent.
1/2 negative 1.
1/2 negative 1. Excellent.
And 1/4 negative 2.
Excellent. Here it is. The inverse function of 2 to the x. So what is left for Thursday?